Laplace transform of ln x. So in this video, we are going to find the Laplace transform of logarithmic function. Before we begin, it's important to know what Laplace transform is. So a Laplace transform for a function f of x is defined as the following integral. Integral from 0 to infinity e to the power minus sx f of x dx. So basically, the importance of Laplace transform is this integral transforms both the differentials and non-differential, that is normal non-differentiated function, all of these into normal non-differentiated functions. So while solving differential equations, you can just take Laplace transform and then do simple algebra and then get back through inverse Laplace transform and solve those equations. So there it's useful, but for us that's not required. Yeah, okay, fine. Now, so this is the definition of Laplace transform. Yeah, and now we need to find the Laplace transform of ln x. Okay, so rather than ln x, it's easier to find Laplace transform of t to the power n times ln of t. So I'll replace x by t. So this one is easier to find out. Okay, and this is represented by the integral 0 to infinity e to the power minus st t to the power n ln of t dt. Now, why this is easier to calculate is the reason is that we already know the Laplace transform of t to the power n. Yeah, and the integral representation is 0 to infinity e to the power minus st t to the power n dt. And the Laplace transform we know is gamma n plus 1 by s to the power n. Now, if we just differentiate both sides with respect to n, so if we just differentiate both sides with respect to n, then we get the required integral. You see, so partial differentiation with respect to n of gamma n plus 1 by s to the power n, which gamma n plus 1 by s to the power n by partial differentiation of this integral gives us the required integral that we need to solve. Yeah, when that is integral from 0 to infinity e to the power minus st t to the power n dt. Now if we differentiate both sides, here we apply a formula for u by v, that is v u dash minus u v dash by v square. So sorry, it's n plus 1, not just n. So we have v and u dash and then minus u and then v dash will be, since it's differentiated on the basis of n, so we'll have x to the power n plus 1 and then ln of s by s to the power 2 times n plus 1. So this is the differentiation. And over here, since this integral is in the world of t, we can just take this n inside the integral. Yeah. And so we can have integral from 0 to infinity e to the power minus st, this is just a constant in the world of n, and t to the power n times ln of e, t to the power n times ln of t dt. So you see, this was the required integral for this Laplace transform, and when we put n equals to 0, we get the required Laplace transform. So we are near the solution now. And now for this thing, we can just divide by s to the power n plus 1 first. Yeah, gamma of n plus 1 minus gamma n plus 1 ln s by s to the power n plus 1. This is the Laplace transform of t to the power n times ln t. And now to evaluate this, we can invoke digamma function. So basically we can take out gamma n plus 1 by s to the power n plus 1 common. So and that leaves us with gamma dash of n plus 1 by gamma of n plus 1 minus ln s, which is the Laplace transform for t to the power n times ln of t. And I think you know that digamma of x equals to gamma dash of x by gamma of x. So you probably know this. So that's what we will apply over here. Gamma n plus 1 by s to the power n plus 1 is equals to digamma of 1 plus n minus ln s is equals to Laplace transform of t to the power n times ln of t. So this is the Laplace transform for this general result t to the power n times ln of t, but this is not what we are seeking for. Now when n equals to 0, we have gamma of 1 by s, and then gamma of 1 digamma of 1 minus ln of s equals to Laplace transform of ln t. And then now we know that gamma of 1 is just 0 factorial, which is 1. And to find digamma of 1, we invoke the most beautiful result in mathematics, that is digamma of x plus 1 equals to negative of Euler-Mascheroni constant plus Hn, where Hn is the nth harmonic number, that is Hn equals to 1 plus 1 by 2 plus 1 by 3 up to 1 by n. This is Hn. And if you want proof of this, it's over here in the tab. Go through this link, and I've derived it from very scratch, from very basic. Yeah. Now if we have this result, we can easily find out digamma of 1. So digamma of, if we substitute x equals to 0, digamma of 1 equals to negative of Euler-Mascheroni constant plus 0th harmonic number. So 0th harmonic number is basically 0 itself. Since we have no terms over here, if it was h1, it would have been 1. If it was h2, it would have been 3 by 2. But since for h0, we have no terms, so it's 0. Okay, fine. And now it's 0, so digamma of 1 equals to negative of Euler-Mascheroni constant plus 0, so that negative of Euler-Mascheroni constant. And yeah, digamma of 1 is just negative of Euler-Mascheroni constant, and Euler-Mascheroni constant is defined as, for limit n tends to infinity, Hn minus ln of n. Yeah. This is definition of Euler-Mascheroni constant, and yeah, we can now proceed. So this is just 1 by s, and negative of Euler-Mascheroni constant minus ln s. So this is the Laplace transform of ln of t, and we can take the minus common out. That gives us Laplace transform of ln t to be negative 1 by s gamma plus ln s. Okay, yeah. So this gamma is basically Euler-Mascheroni constant. So that's the beautiful result, and we have finally derived the Laplace transform for ln of t. Yeah, so this is negative 1 over s Euler-Mascheroni constant plus ln of s. Hope you enjoyed this derivation, and hope you got some new insights on new mathematical ideas and how we found the Laplace transform. And if you enjoyed the video, do like and subscribe. Thanks for watching, and look forward to seeing you in the next video.